Euler Lagrange's equation could be imagined as a piece of magic. Specifically, it could be used to generate complete curves.
For instance, we could use it to find the curve of the shortest path between 2 points. It could be used to find the curve of the shortest time for a bead sliding on a frictionless surface. Also, it could be used to derive Snell's law of light refraction. Finally, it could be used to derive Newton's law of motion and reaching the law of motion, termed as the principle of least action. To understand Euler Lagrange's equations, let's go together on a short journey. We shall visit these 7 locations. To understand the concept of a functional, let's review briefly the relatively simple concept of a function. As illustrated, a function could be visualized as a machine that receives an input x and produces an output y. Note that x and y are frequently scalar values. For a functional, the situation is slightly different. A functional input is a whole function f. The output is typically a scalar. Please check the examples displayed. Pause the video here and make sure that you can identify the difference between a function and a functional. Consider the shown functional termed as j of y of x. You should note the following. 1. The functional includes x, y and y prime. Hence, it does not depend on y only as it was the case in the introductory examples. 2. The integral limits x1 and x2 are given. For a well-posed problem, the values of y at x1 and x2, termed as y1 and y2, should be also given. 3. We have considered y to be the dependent variable and x to be the independent variable. In other words, given the value of x, the value of y should be determined. This is just a reformulation of the definition of y as a function of x. Right now, you should be wondering what is the target of this discussion. Generally, the target is to find the function y of x such that the functional is maximized or minimized. Hence, the problem is to find an expression for y of x. Pause the video here and make sure that you understand the problem. For instance, you should realize that we are not trying to calculate the integral. Instead, we are looking for y of x such that the integral, termed as the functional, is maximized or minimized. Since you have been patient, it seems fair to give you a small reward. The solution of this problem is obtained using Euler Lagrange's equation. Generally, this is a nonlinear differential equation. You may be disappointed for the complex expression of Euler Lagrange's equation. However, Euler Lagrange's equation reduced the original integral differential equation to a differential equation. Fortunately, there are many techniques to solve differential equations and they are generally easier than integral differential problems. Please have a look at the Taylor series expansion of a function f of x. The function is written as a polynomial of infinite order. The following points should be emphasized. 1. The series is written in terms of the function's value and its derivatives evaluated at point x equal to a. 2. The coefficients of the series are equal to the function derivatives. Generally, the most important term is the first derivative and high-order terms may be neglected in many cases. 3. The series convergence requires that x should be close enough to a. In other words, the term delta should be small enough for convergence. Finally, the expansion may be rewritten in terms of delta. Please have a careful look before proceeding to the next part. The concept of extrema could be introduced using the analogy with functions. Given any function f of x, it could be possible to identify the points of extrema. These points are the points of local minimum or maximum. It is well known from elementary calculus that the derivative of the function vanishes at these extrema. Let us return back to Taylor series. Notice how the infinite terms after f of x equal to a could be written as delta f, yellow highlighted. If x is close enough to a, we may assume that delta is very small. Hence, delta f could be equal to the first order term, green highlighted. Further, let us consider the case x equal to a is a point of extremum. Hence, the derivative of f with respect to x will be 0. Hence, delta f will be 0 at points of extremum. It may be useful to visualize the situation. Suppose that you have climbed to reach a mountain top. This is a local maximum in mathematical terms. If you move a small displacement, your elevation should be almost unchanged. This is the condition of extremum derived in the past slide. Let's return back to the concept of extrema. However, let's consider the extrema of a functional. Suppose that you managed to find the extremum of the functional j using some sort of magic. This extremum of j is calculated at y equals y star. Hence, if we change y by a very small quantity near y star, the value of j should not be affected. In other words, delta j in the neighborhood of y star should be 0. It is so difficult to visualize the extrema of a functional like we did in the function. However, the same concept is applied. To be ready for the derivation, we need to introduce the concept of function variation termed as delta y. Let's compare the situations of finding extrema of functions and functional. The quantity delta y for a functional is similar to delta for a function. The visualization of delta y is difficult compared to delta. However, delta y is characterized by 3 properties. First, delta y should be very small. In mathematical terms, delta y should be infinitesimally small and very close to 0. Second, delta y should be arbitrary. This means that delta y can take so many small values near 0. Remember that delta y is small but it is not 0. Remember also that delta y cannot be assigned a specific value. Finally, delta y should satisfy the problem constraints. These constraints are the limits of the integral. Please remember that the values of y were prescribed at the limits of the integral to be y1 and y2. Suppose that the curve that achieves the extremum of the functional j is y star, plotted with the red line. Let's study the behavior of j in the neighborhood of y star. In other words, let us try to calculate j at some function y that is very close to y star. There are many possible values for y of x. However, all these functions satisfy the constraints at the endpoints x1 and x2. Remember that delta y is equal to y minus y star. Let's rewrite j and emphasize that y is close to y star. The key idea now is to use Taylor expansion. This is justified since delta y is small according to property 1. Before proceeding, a subtle idea should be clarified. Specifically, the derivative of the variation is equal to the variation of the derivative. Pause the video and make sure that you understand the derivation. Note that the yellow highlighted terms at the left and right hand sides cancel each other. Hence we can now focus on the delta j term. Next, using the integration by parts, the derivative of the variation can be taken outside the integral. However, the resulting term cancels due to property 3. The integral can be written as a product of 2 terms. The first term consists of derivatives, and the second term is delta y. Remember that we are near the extremum point. Hence, delta j is equal to 0. Since delta j is 0, we need to think which of these 2 terms is 0. However, due to property 2, delta y cannot be 0 because it is arbitrary and cannot be assigned a specific value. Hence, we finally arrive at the Euler Lagrange's equation.